since we had the delay. Hopefully some people can stay longer if possible. But anyway, all right. So I was saying, feel free to reach out to me. This is all my contact info. I will share the slides with Tayobit and Julie and Paresh, and then they can redistribute as well as necessary. So the agenda, we're going to talk about the fundamental characteristics of Cosmos DB from the perspective of people that work with SQL Server. So that's what I try to do, is to leverage people that know SQL to get people interested in Cosmos, and hopefully you try it out, you learn a little bit about it, and it's something else that you can say that you know, which I think is a win-win for everybody. So we'll cover Cosmos DB versus SQL, how you manage performance, consistency, which is very different from the SQL Server experience, a little bit about security, SLAs, and recoverability in Cosmos, which basically is, how do we do what's in there for backups, HA or DR, and a little bit about the cost. And I have demos as we go along. I have a utility that I built and I updated with the help from a couple of people from Microsoft for the demos. It's just open on GitHub, so I'll have the link there as well. You guys can download it and try it out if you want. Prerequisites, SQL experience, pretty much, that's it. First is obviously, I had this conversation a bunch of times when Cosmos DB was introduced, that people started to say, like, well, is Microsoft just moving into this direction with NoSQL? Is SQL Server dead? Is the relational database dead? And of course it's not. It's just different tools for different problems, right? But they are fundamentally different, right? And that's where first it's important to understand what is the NoSQL, NewSQL movement. It's been there for a while now, but I still see a lot of people struggling sometimes to figure out when to use one type of database or the other, right? So the main value proposition of NoSQL or NewSQL, depending on who you talk to, is that you can scale horizontally, right? You add more nodes, and this could be commodity server nodes. It doesn't have to be a special machine. And instead of, continuously beefing up one node, right? If you have a client that has, a large OLTP read-write database on SQL Server, for example, as they grow over time, what happens is they start with, X amount of cores, X amount of memory, and then over time they have to use 2x cores in the same machine, 2x amount of memory, and then one node just keeps getting fatter and fatter and bigger, and it becomes almost like a single point of failure, right? So the idea is we scale out, right? We add more machines as opposed to scaling up, just increasing the capacity of one machine. So there's, if you have multiple nodes, that the database is distributed, you can have more availability, right? Because the nodes can replace each other, and scalability is technically supposed to be easier because you just have to add machines, but the data needs to be replicated around. So there's a certain amount of problems that are better solved with NoSQL databases, especially when the data space can be uniformly partitioned. And when it's not, it's, in my opinion, better to just stick to a relational database and try to do some of the more modern stuff like, read-only workloads, scaling out through replicas and things like that, right? And I'll talk about this a little bit more as we go through the slides. And then another thing that is very common with NoSQL databases is that the application clients can decide on different levels of consistency. And basically what that boils down is to asking yourself, do I want the most truthful data, so the data that is most up to date, or do I want the data to be returned fast? Historically, the NoSQL databases popularized the term eventual consistency, which most people are familiar with, which just says, if you wait long enough, all the copies of the record will eventually converge on the same value, right? But there's no guarantee. Eventually, it's literally what it says. It's eventual. If we look at this from the SQL Server perspective, so some people will say, well, SQL Server can scale out, right? You can do multi-master peer-to-peer replication, for example. I don't know if you guys ever tried this, but peer-to-peer replication is not really a solution that scales very well, in my opinion. I've tried it with clients on my career, and after 2 or 3 nodes, it's just the whole thing just bogs down. The conflict detection is pretty bare bones, in my opinion. And it just was not a good experience. SQL Server, main reason for this is that SQL Server was not built out of the box to be a distributed database. So these other systems that are built on top of it like peer-to-peer replication, are built on top of what was designed to be a non-distributed database and try to add some of these capabilities on top, and that's why it doesn't really scale very well. Now, a more popular design has been the one master many read copies design of the availability groups, right? So we have one instance that does read and write, and then you have other instances that do read only, right? And that's what I mean when I usually, if I look at a client that is really high traffic, high volume on SQL Server, this is the design that most people are going to right now. Is they try to have a beefy server to do the read write, which would be like instance 1 on the screen, and they try to have other machines that will do just the read only for queries and reporting. I had a customer that in Canada that does a lot of online retailing, and they had this type of setup to do. They did several dozen thousands queries per second, a large online storefront, and it was one read write, and the rest were all read replicas. They had 4 read replicas. So this works well as long as most of your workload has to scale on the read side. NoSQL scales on the other side, and when I say NoSQL, this includes the vast majority of NoSQL databases. They behave in similar way, Cosmos DB not being the exception. So what they do is you take the database and it's partitioned by hashing a key, and you select what the key is. So you have, a certain node, and all these nodes, they can all do read and write. So it's not like the SQL Server one where just one node was able to do read write. In NoSQL databases, all the nodes can do read and write, and they all talk to each other so that there's multiple copies of the data. And this is the same scheme used by Cassandra, Mongo, Cosmos DB. They all do the same thing. They take the data, they partition it by taking a key and hashing it, and then says, okay, so you said that the key was going to be the username. Okay, so username, Warner, it hashes to node 3, and it goes, all the Warner records are going to node 3. And then user Julie is hashes to node 2. All the user records for Julie go to node 2. And that's pretty much how it works. In terms of APIs, there's a big difference here. So SQL Server, we mainly interface with it through T-SQL. And it is a relational system, right? You create a bunch of tables, and then you set relationships between them, and the system will defend the integrity of all these things. And over time, not just SQL Server, but pretty much every single commercial database over time has added functionality on top of this core relational engine, right? So SQL Server, for example, now has XML built on top, has JSON built on top, it has graph capabilities built on top. But all that is basically a programmability layers built on top of that relational engine, right? Cosmos DB is similar in a way. It has the document database that is the core original engine of Cosmos DB. And then on top of that, Microsoft has developed a bunch of other APIs so that users from other systems can make it really easy to migrate and leverage Cosmos DB's capabilities. So the document database, it's also known as the NoSQL API, is really the core of the product and the offering. But there's also MongoDB compatibility API, so you can connect Mongo clients to Cosmos DB. There's a key value API that uses the Azure Table API. This was an older Azure service that was built on top of blob storage to create really big tables that you could interact on key value pairs. That's in Cosmos DB now as well. Graph through what's called Gremlin. Gremlin is the language that is used for the Graph API in Cosmos DB. It's an Apache project. There's a white column API, which basically is the Cassandra compatibility API. And finally, and this was, I think this one is from last year, there is even now PostgreSQL API that you can connect a PostgreSQL client into Cosmos DB and basically simulate like Cosmos DB is a PostgreSQL database behind the scenes. I haven't tried it yet. Very interested though in this because I think it's an interesting choice by Microsoft. Let's say I haven't tried it yet, but we'll see. We'll see if it gets adoption as well. So logical structure. When you talk about SQL Server, we have the instance. The instance will turn into the database. The database, we have tables, and then inside the tables we have the records, right? Cosmos DB has a Cosmos DB account. Inside a Cosmos DB account, you have a database. This database will have a collection. Collection is what is mostly similar to a table, let's say. That's the most equivalent thing to a table. And then the collection actually can have store procedures, triggers, UDF. So that part is a little bit different. If you see in SQL Server, the database is the one that holds these code modules, whereas in Cosmos DB, is the collection that holds the code modules. And then inside the collection, I put here documents, but it really they're only documents if you're using the document database, right? They are at the end of the day records as well, but these records have different roles depending on what API you're using, right? So this is what I call the Cosmos container, right? The Cosmos container can be a collection of documents if you're using the document API. It could be a graph if you're using the graph API. It can be a table if you're using the table API or the PostgreSQL API or the Cassandra API, right? So these containers, they play different roles depending on what they are. But regardless of which API you select, behind the scenes, what happens is the service takes that container, it takes the data that is going into that container, same process as I mentioned before, it hashes the key. And if your key hashes to, let's say in the diagram here that I have, if the key hashes to a value between 1 and 100, it goes to node 1. If your key hashes to the value between 100 and let's say 2000, then it goes into node 2, and so on and so forth, right? So that's the way that it works. And using this particular scheme, you have technically unlimited storage and unlimited scalability. Now, of course, there's limits to everything because Microsoft hasn't figured out how to defy the laws of physics, but the limits are pretty big, right? So at some point you would hit some sort of node limit and you would have to call probably the Azure support and tell them that you hit some of these limits, but the limits are fairly large, right? The container then, as I mentioned here, is the entity of space and optionally performance. And I'll talk a little bit about that, how performance is managed and provisioned. And you can make the container also the unit of performance if you want to. So transactions as well in SQL Server, this is something that you do all the time. They can cross tables, they can even cross databases, right? You can, if you have two databases on the same instance, you can do a cross database transaction really easily. I mean, Microsoft even has the MSDTC if you even wanted to do cross SQL Server transactions across instances, right? You can do them with T-SQL. You can do them with in a module, let's say, by just creating a transaction inside a store procedure, or you can initiate a transaction through .NET code, or you can just do it ad hoc. You can type in begin transaction, submit, then type some SQL, then commit or roll back in the end, right? Cosmos DB, the transactions are scoped in a container or in a single partition. Now, there used to be this idea of a fixed container. I think this actually has been retired. Now you will only find references to partitioned Cosmos DB. In this case, the transactions are limited to a single partition. So what that means, let me scroll back down, is here in this diagram, you know, I have node 1, partitions 1 to 100. So if I, let's say I'm using username as my key for my Cosmos DB container, then, you know, username Warner always partitions to the partition 100, which is in node 1. That means that my transactions always have to be scoped to that partition. So everything that I do in a transaction has to be scoped to the data for Warner. So you guys can see now how that already gives us an idea of the universe of applications that you can use for Cosmos DB, right? So in a relational system, you sacrifice the flexibility and the scalability because you can't scale out indefinitely by adding more machines, but you have lots of freedom as to how you want to apply transactions, as to how you want to join things, right? Because everything's in one machine. Whereas in a distributed database, you are gaining flexibility and you're gaining performance or scalability, but you are sacrificing the fact that your transactions are going to be scoped to a single partition, and your queries they can go across the nodes, and Cosmos DB supports that, but that's going to be way more expensive than if you just had, let's say, like one big SQL Server, right? So the system, while it can do that, it doesn't really perform the best. It's not where it shines the best when it's doing cross partition queries. Okay. So turbo button, how does that performance work? So a performance model is you define throughput by request units per second for the most part. So I said here, operations consume a deterministic amount of request units. So every time you do something, it consumes a similar amount of request units. Mongo is the exception. This is something that is pretty new, and it is the fact that Microsoft has introduced a Cosmos DB flavor that you can do for the Mongo compatibility API of deploying with cores. So right now that's the exception. So everything else works with request units, but they have introduced MongoDB, Cosmos DB for MongoDB with cores. So the idea there is that Microsoft wants to make it really easy for Mongo existing customers to just size up their Mongo clusters and then say, well, I'm using, let's say, 16 cores in my MongoDB right now, so I can just do 16 cores of Cosmos DB. So right now, that's the exception. For the most part, if you use the document database API right now, for example, most people would just go ahead and use request units, and it works pretty well. It's really flexible and it's really fast as well. I'll show you guys in the demo in a second. So it can be provisioned or serverless. So you can actually say, I want this many request units, or you can say, I just want to do serverless Cosmos DB. So serverless Cosmos DB, right? If you're not actually running a workload, it doesn't charge you for any compute. However, if your workload is 24/7, then serverless will end up being more expensive than if you just provision the right amount of request units, right? Request units, you can provision at the container level. So it could be at the collection or the table level, or it can be provisioned at the database level, and then you would share amongst the containers. So the shared, the database level is more similar to what you would see with SQL Server. But it has the option to, let's say, imagine that in SQL Server, you could say this particular table gets this many resources. That's also what you can do with Cosmos DB. And consumption, like how many resources you're consuming, depends on the item size, right? The record size, the container size, how big your table will be, for example, the consistency that you're using, and we'll talk about that in a second, and the indexing that you're using, if it's strong or not, and the query complexity, right? If you're writing something really complicated, then obviously you're going to consume more request units, right? Key partitioning. So the request units are split by physical partitions. For example, if you have 2,500 request units and 25 partitions, you get about 100 request units per second per partition. The important thing here to remember is to try to you have to select a key that will distribute well and uniformly, right? So let's say you have an online service system that you're doing something for users. Let's say the users are keeping their grocery list. I just made that up. And then you have, let's say you're operating in the United States. The United States has 50 states. Partitioning key of state is probably a really bad choice, right? Because there's some states that have way more people than other states, and you're going to produce an accumulation of data in a particular key range, right? A better selection for the key might likely be just the username, right? Or a user email or something, so that all the users, the same users' recipes are always in the same spot, or the grocery list, sorry, are always in the same spot, right? So you have to pick something that will distribute uniformly. That's the ideal. If one partition is a lot busier, then it becomes a hotspot, limits the scalability of the system, right? So, and current guidance is to try to make a single partition not bigger than 10 gigs, right? So what you don't want to do is one node be overloaded while the other ones are just basically not doing anything. Indexing, all properties are indexed by default. There's a big change from SQL Server where you have to be really surgical on your indexing. By default, they're all indexed. However, you don't have to accept the default. Having everything indexed obviously affects space. It affects request unit consumption. You can have different types of indexes, hash indexes for point lookups. You can have range indexes for less than or greater than searches. And there's also spatial indexes, which I think is pretty cool. that are used for some of the geometry and geography stuff that you can do with Cosmos as well. They can be updated in a consistent fashion, or they can be lazily updated depending on your application requirements, right? Consistent means as soon as you change the data, the index is changed right away, right? Or it can be lazy, so the data gets updated and then there's a background thread that can just go and update the index behind the scenes. And basically that becomes more like eventual consistency. Or you can just have it set to none. It's kind of weird. You'll say, why would I want an index that is never updated? But the way that you can see this is, I've never used the none to be updated, but you can do things like, for example, just build the index, and then the index is kind of like a snapshot. You can do some loading of the data, and then once it's ready, then you enable the index again to be updated. I guess that would be like one way to do it, because I haven't really had to use that none option at this point. And there's two modes: automatic. Again, automatic is just the index is always getting updated, or manual, which basically is, you know, the index just will get updated when you trigger it with a command. The changing of indexing is always online. So when you change an index policy to a new index policy, let's say you want to go from the default of all the fields to only indexing one or two fields that you know are used, and you change the index policy. While the indexing is changing, the system is always online. It doesn't have an impact on your consumption. So it's not like your requests are not going to start failing because of that. And the only thing is that the contents of the index itself are going to be eventually consistent while it's being transformed. All right, so I'm going to jump in the demo and I'll show you the utility. And like I said, there's going to be a download link in the deck for the utility as well. So let me see, where do I have my machine here? Here it is. So I have this utility here. This is lost my mouse. Oh, wait. All right, there it is. So I'm gonna try to do this without being able to see the, minimize this. Looks like the screen share probably took away the mouse on my screen. This is weird. You can see where it is because of the highlighting. All right. Oh, all right, let's try to do this. It'll be tricky. So you guys see there it says Cosmos demo, country name Canada. This is just a small utility I have. It generates a workload against the Cosmos DB database. How many? It says artists because it's supposed to be like a music service, and I have other presentations I've built around this demo. So like you have like a dashboard where you can see like the most popular artists and whatnot, and I use this utility to generate the data for that as well. But for the purposes of today, we're just going to use it to show some of the Cosmos DB characteristics, right? So let's say, for example, I have an amount of artists. Let's say I just have one artist, just to show like what the tool actually does. Oh, my mouse is back. Good. Amount of artists, let's say one. Calls per second. This is what the utility does. Let's say I want to do 1 call per second, and then I just want to do it 5 times, and I go start right, and you see what the utility has done is basically it picks an artist from like a list, and then it writes a record that says, you know, this is how many listeners this artist has right now, and then it tells us how long it took, like 1.01, and consumed an X amount of request units. So as you can see here, each writer is consuming about 15 request units or so. We did 5 successful calls, and you see it right here, and we didn't get any exceptions, right? So what I want to showcase here is the whole idea of request units, right? You can see here, we're consuming this much. I can reset this, for example, and make it beefier, and run a heavier workload, right? So let's say 10 artists with 20 calls per second, and let's do that for 5 seconds. And let's start the right workload again. And we'll see how long that takes. Now I obviously added a lot more to the workload, so this is going to take a little bit longer than the previous one, but it should complete in about 10 to 15 seconds or so. there. And then you can see here now, there's a bunch of different artists, right? Because I think I selected 10. And we had 591 successful calls, boils down to about 36 calls per sec. But you can see right away here, we have 30 calls with exceptions. So I'm running Cosmos DB right now with resources provisioned at the container level. And it's 400 request units per second. You can see some of these, they already hit, in a particular iteration for one artist, it hits 265 request units, 296 request units. So what's happening here is that every now and then our utility demo, this tool that I have right now, is trying to do more than 400 request units per second, and it's getting, in this run that we just did, for example, it got 30 calls with exception. So 30 times it tried to write, and Cosmos DB threw an exception that said basically, hey, you got to stop. I don't have resources right now. You get denied, right? So that's pretty much what it means. Now, what I want to showcase here, though, is how quick we can resize the system. So I can do resize 800, and immediately I get more resources assigned to my Cosmos DB database, and I can rerun that same workload, and hopefully we'll get a better outcome in terms of the performance of that particular workload, right? And sometimes, you have to, depends on what you're trying to do. Obviously, I just came up with that number of 800, but you can see immediately right away, right? So now we had way more successful calls. We can see the average throughput went up to 64 calls per second, and now we only have 4 exceptions in this particular workload. So if I pumped it up again to, let's say, 1200 or something like that, then we would get 0 exceptions. We'll push the throughput and so on. There's the point of diminishing returns, obviously, right? There's the point where I could add more request units, and as long as I'm not pushing the workload, then I'm not going to get better performance anyway. But we can see the difference here just by moving from 400 to 800. We go down to from 30 to 4 exceptions, and we went from 36 to like 90 something successful calls. Sorry, it was 500 successful calls to 900, and from 36 average calls per second to 64 average calls per second. So a big jump. And what I want to highlight especially is how quickly the system responds to your requests for more resources, right? Because of the distributed nature of it, your Cosmos DB database is basically spread around a bunch of different Microsoft nodes, and they can give you more resources on each one of those nodes. And as long as the data is distributed well, then it responds really fast to more requests for more resources, right? Which is not the case with Azure SQL, for example. If you try to use Azure SQL database and you want to move from 2 cores to 4 cores, you gotta update it on the portal, and then you gotta wait a couple of minutes for your database to be brought down, to be put on like a new container, a new VM. I don't know how they do it behind the scenes, and then being brought back up, and that takes a while, right? It's not as instantaneous as how it is here, right? I'm really happy my mouse is back though. Hopefully it stays like that. Now I just want to touch on consistency because it's very important to Cosmos. Do you want the most truthful data? Do you want the data as fast as possible? And Cosmos is interesting in how it handles this. And the main question is, why can't I have both, right? So why not both? So in a single data center, it's not a huge problem, or really close data centers, because data is replicated really fast and the values converge in milliseconds. However, if you're building a geographically distributed system, then you have to deal with the laws of physics, and there's only so, as fast as light can travel. And on top of that, you have to add all the latency of the systems around it, right? So Cosmos from the beginning was built to be a global distributed database. So the team took this as one of its fundamental design tenets, so that Cosmos DB would have this flexibility to be able to do geographically distributed replication and have options for how you want it to do it, right? So it has multiple consistency models. On this side, we have, on the left side, it says more fidelity, higher latency, less availability. On the other extreme, that would be eventual consistency, totally eventual. It says it's less fidelity because you don't have guarantees, but it's lower latency and it's more availability because the data can be picked from more different types of nodes. So this goes from strong. Strong says I want the most truthful thing always, to bounded staleness, which says I'm okay with a little bit of delay, but up to a limit, to session, which basically says I want to make sure that I can always read my own latest data. Consistent prefix, which basically says I'm okay with the data not having a guarantee of how old it is, but at least it has to be read in order, at the right order. And then eventual just basically says whatever. At some point in time, it will converge to the right value, but you don't have guarantees of how long ago that was or whether you're reading values in the order that they actually happened. So I have an example for this. So I use this as the thought process to figure out what these consistency level means. So let's say you're doing a flight from La Paz in Bolivia, the capital city of Bolivia, to San Jose, the capital city of my country of Costa Rica. And this flight path actually overflies the country of Colombia. So if you're familiar with South American geography, you can visualize it. If not, I have a little map coming up. So, and let's assume that we're going to query Cosmos DB in two different regions in the continent. One is in Brazil and the other one's in Canada. And we want to know is what was the last city that the plane flew over? Okay. So this is Colombia, right? And the plane is exiting Colombia, and it's going to enter Bolivia, and then it's going to go into Costa Rica, and it takes a trajectory like this. So it's going to go over the capital city of Bogota first, and then it goes over a very famous city in Colombia as well, called Medellin, right? So it has, in reality, the plane goes first Bogota, then Medellin, right? That's what really is happening. But that might not be what the system will tell you because it's a distributed database. So let's walk through that. Right? Let's say the plane is right there right now. So the last city, as a fact, the last city that it went through is Medellin. All right. First Bogota, then Medellin. So let's do an example of strong. We know that the plane just went over Medellin, Colombia, and sent a message, let's say, to the Brazil Azure region. If the application in Canada needs to do a strong read, it needs to read Medellin, then this requires reading the Brazil database, or it requires the write from the message on the plane to be double committed, both in Brazil and in Canada. So you guys can see how right off the bat, doing a strong read will either have higher latency or it will be slower in general, right? If we say it's bounded staleness, so I'm okay if it's older, but it has to be up to a limit. So let's say the plane went over Bogota 45 minutes ago, and just 10 minutes ago, it went over Medellin. And then the app does a query that says bounded staleness of 30 minutes. All right, so I want to know what it was 30 minutes ago. So in this case, because your boundary is 30 minutes, it might read Medellin, or it actually might read Bogota. But it would still respect this consistency requirement because you're asking what it was up to 30 minutes ago. If you brought it down, and you said, no, I wanted bounded staleness of 10 minutes, then you would get a guarantee that we would read Medellin, right? So this one allows you, bounded staleness allows you to move that limit and gain more scalability depending on how long you can wait to have the most truthful data. Session, it says I always want to read my own messages. So basically what happens is the plane went over Medellin and sent a message to the Brazil Azure region. And as long as the plane keeps, the session connected to Brazil, it will always see its own data, basically, right? So session only works for you as yourself being able to read your own data. Consistent prefix says, I will always read in order. There's no guarantees as to how old it is, but you will always read in order. So it would always tell you, let's say you do a bunch of those queries to check what was the last city that the plane flew over. In consistent prefix mode, it will always read Bogota first, and then at some point it will read Medellin first. But very importantly is that it will not read Medellin first and Bogota later, right? Because this would actually give you a view of reality that is not correct. The plane never went over Medellin and then went over Bogota, right? And this is what eventual consistency opens you to. So the most relaxed consistency that is again, the most popular term out there you find on the internet is eventual consistency. But the problem with truly eventual consistency is that you technically can read things out of order, right? So the application, depending on the node that it connects, it could read Bogota, and then it could read Medellin after, and that would be okay, but there's no guarantee. It could just as well read Medellin first and then Bogota after, which is what a lot of cases you don't want. It depends on the type of query that you're doing. In the example of the plane, if you really want to follow the flight path, then obviously eventual consistency would not be a good choice. All right? Nice thing is, I mean, you just have to understand what they are, but you don't have to understand or try to figure it out how to implement these yourself. Cosmos DB handles this under the covers. As a potential admin or an operational contact to somebody that is going to be in charge of a Cosmos DB solution, what is important is for you to be aware of the difference between these consistency levels so that you and the developers, or if you're the developer yourself, at least you know what you're playing with, and you can all talk the same language and understand these concepts, right? But the nice thing, again, it's all handled under the covers. You just have to specify the consistency level that you want to use, and Cosmos DB will figure it out behind the scenes. Okay, now I just want to show here quick the impact of consistency in the throughput, because they go one by one together. So if you guys see here, so I have, I can do a read workload with my utility as well. So I'm going to reset it just to make it really clear. We're just going to do one artist, and we're just going to do 1 call per second, and we'll do 5 seconds. And we're going to do a read workload. So you guys can see I have this iteration of 0 to 4. Artist is called Jack's Mannequin. Never heard of this artist, but you know, it's there in the database. Completed and consumed 4.5 request units. 4.5 request units. This is by default, my account is using what is called bounded staleness. So if I go into my Azure portal, you see here, this is my Cosmos DB account that I'm using for the demo. And by default, it's using this bounded staleness. Now, strong bounded staleness, they are considered the more expensive consistency levels. So they have a certain request unit cost that is higher than the other ones. So I'm going to switch, for example, my consistency to Eventual in the utility, and just rerun the workload. And we'll see right away, and you guys can see on the screen, I'll zoom in a second. You see right away here, right? So the consumption of request units goes from 4.5 to 2.25. So basically, Cosmos is saying if you can live with the eventual consistency, or even with consistent prefix is also cheaper. If you can live with that, then you will get a lot more throughput out of the system, right? You will be able to put in as many as double the amount of reads than if you pick bounded staleness or strong consistency. Okay, so that's something to keep in mind. If you can get away with using some of the more relaxed consistency levels, then you'll get a discount there in request units, right? All right, and yeah, we'll probably go a little bit over the hour. Apologies for the technical issues, but not too bad actually. So let me just finish up here and have one more demo to do it. So locking it down, security features, familiar to SQL admins for the most part. So you have encryption at rest, encryption in transit. There's IP firewall support. You can also use a service endpoint to connect to a particular VNet. There's database auditing. You can do a database access control with Azure IAM roles to give them access to a particular database or collection. Or you can use a master key for the Cosmos DB account as well. Or you can also generate resource tokens through the API for temporary access to Cosmos DB as well. Recovery features, backup and restore. So point-in-time recovery is supported. It didn't used to be supported, but it's been supported now for maybe like a year or something like that. All operations are backed up asynchronously within 100 seconds. So it's very nice RPO, very quick. It's a little bit less than 2 minutes. And retention, you can select of 7 to up to 30 days of the recovery time. If you delete your account, they're kept for 30 days. You have to call in support to bail you out if you do need it after that. You can also do it self-service restore through the portal or PowerShell or the Azure REST API. This did not exist before as well. It used to be that restore was only done through support, but now there's self-service restore capabilities. So you don't have to go back and open a support ticket if you want to restore your Cosmos DB collection. Okay. HADR. Well, HADR is built in as a core service capability. So single region HA is provided in the basic service. As if you go back to the architecture diagrams that we saw before, right? All the nodes are talking to each other, always in the same region. So that's just how Cosmos DB works in general. There's always going to be high availability because of its distributed nature. DR can be achieved through geo-replication. And geo-replicated copies are very cool in Cosmos because they're not just for reading, so it's not just for read scale out, but you can also write to them as well and get really low latency for local applications, right? And it's available across dozens of Azure regions. It's considered a Ring 0 service that Microsoft, that's the term Microsoft uses for services that are critical, that have to be deployed in every single Azure region. So sometimes there are services that they say, oh, it's only available in region X, Y, and Z. It's not available in this other region. Cosmos DB is available in every single region that Microsoft puts out in the world. I'll show you the demo real quick of what that looks like. So, this is my task manager here. So, if you guys see here, actually, I can say replicate data globally, and this is very nice, very easy to understand diagram. So you guys can see here, I have one in Canada. I think I'm using Canada Central. Yeah, Canada Central right here. And this one is actually geo-replicating all the way to Japan East. And you can see here as well where my Japanese copy is also enabled for writes. And my utility that I have here, if you look at my consistency right now, so I want to show you that because that's something that's very neat as well. My guarantee for consistency right now between Canada and Japan is bounded staleness by a maximum lag of 5 minutes. So the guarantee, so this is the SLA, is that at the most, we will be 5 minutes behind between Canada and Japan. However, the reality is usually a lot better regardless. So I have a way here in my utility, I can execute this query. When I do this exec query, what it's doing is getting the most latest record that was written into my Cosmos DB database. So you see here, the last one that was written has this country here as Canada. And if I look at this particular utility that I have on right now, this is my global endpoint, cdemos.documents.azure.com. And you see here it says read regions, Canada Central, Japanese, write region, Canada Central, Japanese, Canada Central being the priority one. And you see here where it says Cosmos application region is not set. So I'm basically telling Cosmos I don't have a preference. It will just pick Canada Central by default. However, I also have a VM in Japan. So this one is in Japan right now. I'm just going to say one artist, 1 call per second, and 5 iterations, let's say. And I'm not going to start it right away. I'm just going to show you here status. And you can tell even the lag is higher on my screen because this one's in Japan. So the same config, right? I'm connecting to the same global endpoint. It says Canada Central, Japanese, Canada Central, Japanese. Cosmos application region is not set because I haven't enabled the geo writing in my utility here. But if I type here geo write, so now it says geo-replicated writes, our preferred region is going to be Japan East. Let me go back and grab the status, and you'll see now it has the application preferred region properly set on Japan East. And if I start my write workload, let's do it now. So now it's writing locally to the Japan region from my Japan VM. And remember the 5-minute lag. However, I'm going to move right away into my Canadian VM. And I'm going to run that command to see the latest query. And we can see we already have records from Japan. Okay? And you can see the timestamp here. It says 18/0/20. It might already have finished replicating everything. You see 0034, 0041. So here they come, the Japan records. 45. and so on, right? So point here, very easy to do geo-replication with Cosmos DB that can support writes as well. Big difference, huge difference from other products out there in the market. And even though there's a guarantee of 5 minutes, usually the latency is a lot lower than that, right? A lot lower than 5 minutes. Okay, and then just to wrap things up, if you do want to try it out for free, you can go to azure.microsoft.com. Well, the link is there. Try Cosmos DB, and I think you get like a couple of free days of Cosmos DB to just play around with it. If you want to try out the demo utility, you can find it on that GitHub link, and you can pretty much just do the demos. You can follow the code as well. It's really built for learning, right? It's not production grade. Don't try to use it for any production work. But you'll be able to do the stuff that I was just playing around with it today. So it gives you something to play around with, pretty much. All right, and then yeah, let's switch over to questions. I don't know if we have any questions right now.
No, I do not see anything, but I want to thank you. Thank you so much for taking time and speaking. So for the attendees, if you have any question, please put it in the chat. Warner agreed to stay a little bit longer to answer any question if you have any.
Yeah, if you have anything. If you don't have anything right now, also feel free to look me up on LinkedIn. I love to connect with everybody who joins my sessions. People send me messages all the time. They ask me stuff. Sometimes I even give out career advice, anything that I can help with. So feel free to add me. And if you think about something related to Cosmos DB after, yeah, just send me a message over there as well. Sounds good?
Okay, I'm going to stop the recording.